So today's topic is global regular functions. On a projective varieties, constants. So this is the result. So recall. So what is a projective variety? So it's some irreducible closed subset in some Pn, right? And Pn is, you can write it as union of Ui, where IUIs are the affine open subsets. So each Ui is some, you have some phi I think notation is phi I or psi I, I don't remember, Ui to some n, right, for each psi I. For I equal to 0 to n. Right. So what we want to prove? We want to prove that the functions, regular functions on y, they are constants. That there are no other regular functions. So y. So if y is a projective variety, so with y you can associate as the homogeneous coordinate ring. So this is basically K. The field is over. The varieties are over field K. So K x naught x n modulo some prime ideal IY. I am writing it as IY. The homogeneous IY is a homogeneous prime ideal, right? What is homogeneous prime ideal? Means it is generated by homogeneous elements, right? Now what you do, now you can, so you Y is a subset here, closed subset here. You take intersect with UI is a open subset. Each UI, so these UIs are open in Pn, right? So this is open. So Y intersection UI. So UI is, so this is Y is a closed subset. So then this is a closed subset in UI, right? So now if I call this yi, now first to check, or I will put a small exercise here, that I can talk about yi is a closed subset of ui. Ui is a affine space. So that means yi is a affine variety. Since y is irreducible, check that yi is also irreducible. So the first is that yi is an affine variety. So whenever something is affine, the homogeneous, what is the coordinate ring of AY here? Coordinate ring of AYI. So coordinate ring AYI, and AYI is nothing but isomorphic to S. This is OYI. Yes, this is same as OYI.
The projective variety is covered by a finite union of UIs.
Yes.
You are using compactness in some sense.
This is the not basic open. These are all standard affine open subsets.
No, but it's called the finite union.
Yes, so UI is basically, you consider UI is, you consider x naught, x1, xn such that xi not equal to 0 or xi equal to 1. See, this is or xi equal to 1. So basically UI is At the ith position, you put just 1.
And rest it can vary.
It can vary, and that is a homeomorphic. You saw that it is a homeomorphic to AN, but the point is not only homeomorphism, this is a isomorphism.
Isomorphism for N.
Yes. So that is your UI, and they are finite. So now AYI. Now what is AYI? AYI is a ring, right? It's a coordinate ring of YI. YI is a closed subset of UI. So what is AYI? So AYI is nothing but S of Y, the degree 0 part. So this is the subring of SY of XI. XY is a homogeneous ideal. It's a subring. It's a subring because if you take 2 degree 0 element, so now you see that the degree, the grading is important, because degree of 2 thing f by g, you define it as degree of f by minus degree of g. That's how you define for the. No, for any f element. So this is you are inverting some elements, right? So for example, degree of f by some xi power m, then this is nothing but degree of f minus m into degree of xi, but degree of xi is 1. So which is nothing but degree of f minus m. So degree 0 part means it is so elements are of the form homogeneous of degree 0 elements. So you say f by some f by xi power m.
So it's kind of some localization.
No, localization is a sy xi. You are localizing, you are inverting xi, but here you are taking degree 0 element. So element of this looks like f by xi power m. F is in sh of y, so that means f is homogeneous, and degree of f is nothing but m or mi, say for various m. S is a homogeneous ring. Sy is a homogeneous ring. F has to be homogeneous. Otherwise, the f has to be homogeneous, because after all, these are all functions on.
Can the elements have negative degree in Sy of localized at Xi?
Yes, it can have 1 by xi power m. If I take.
Can have negative degree.
Yeah. But what we consider is elements of degree 0.
But here, negative degree also makes sense. Like
Yeah, negative degree makes sense. Clear. So now what you have to do? So this is an exercise that yi is an affine variety, and the coordinate ring of AYI is given by this. It's just using this isomorphism. So here you know, right? If you take a closed subset, so the closed subset will go to some closed subset somewhere, right? So use this correspondence. How you, so there's exactly same way you can prove that this is okay. Leave it as I'll leave it as an exercise. Okay. So in general, so this is in general. Suppose S is a homogeneous ring. So this is a notation. If S is a homogeneous ring, and P is a homogeneous ideal, prime ideal. You can mostly we will work with homogeneous prime ideal. then you consider the localization SP. So now, and this is the localization of S at P, homogeneous prime ideal. You can talk about the S round bracket P of S. So this is the subring of the form A by F power m, where A is homogeneous and degree of A equal to m. Degree 0 part of the local ring.
No, I'm saying degree 0 part is
No, 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 no. It won't be local ring. Local ring of what?
degree 0. Oh no, that T has to be like all the non. I mean, the multiplicative closed set has to be like the or homogeneous elements.
Localization at which ideal? So whenever you take, see, it is of the form, it is not localization at some prime ideal.
Local ring.
Okay, so okay, what is the maximal ideal of this?
That S inverse P. I'm saying T inverse P, where T is all the homogeneous elements not contained in the prime ideal.
Okay. So question SP local ring. So if you this is subring of a local ring, right? So are subrings of local rings are local rings? Okay, so check that. Okay. So this is, but the point is that this will play a role in the in proving that constants are the global functions are constant. Okay. 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 So let's recall what is the function field k of y. Yeah. So k of y. So these are the ring of regular functions, right? U is open subset in Y and F is regular. And with some equivalence relation that U1 F1 is equivalent to U2 comma F2 if F1 restricted to U1 intersection U2 same as F2 restricted to U1 intersection U2. This was the function field. Now what I so now what is the function field of k of y? If y is a projective variety, so again this I leave it as exercise. So if y is projective, then function field of y, again this is nothing but sy. You invert the zero ideal. Zero ideal is a prime ideal, right? Because after all, y is a irreducible variety. So it's an integral domain. Sy is an integral domain. So you take the quotient field of sy, but take the degree 0 part in the quotient field. Degree of any function in the quotient field, it makes sense because it is of the form a by f power f, degree of a minus degree of f, right? So take the degree 0 part. So this is and this is one part. Another part is that you can talk about the for every point P in Y. So by Hilbert-Nurserin says it corresponds to some maximum homogeneous prime ideal of Sy, right. Now, what is OYP? You can talk about the stock of regular functions at the point P. Then this is nothing but Sy of MP, degree 0 part of the localization. So MP is a homogeneous prime ideal, and take the degree 0 part of that. That is the so point is that whenever you think of regular functions on projective variety, you just consider the degree 0 part, because after all the function should be defined on, I mean, it's on lambda x and x, they should be same. So f by g of lambda x, so intuitively, if you define something, f by g of lambda x is f of lambda x by g of lambda x, right? By f, g are polynomial, but to be defined, f and g has to be same degree and they have to be homogeneous. That is why always you have to take this degree 0 part. And here grading is important, you see. You are putting a grading because you are defining degree. Degree plays an important role. So last class, I think you asked that why grading is important. Grading is important in this to define functions.